Hi, my name is Linmei Shang from the Institute for Food and Resource Economics at the University of Bonn. Today I will talk about adoption and diffusion of digital farming technologies.
We know that digital farming technologies might lead to more productive and sustainable agriculture, but this requires successful adoption and diffusion. As agricultural economists, we are interested in what are the determinants of adoption. This research aims to better understand the mechanism of adoption and diffusion of digital farming technologies, combining farm-level and system-level perspectives, and to provide a conceptual basis for modeling the adoption and diffusion of digital farming technologies. We will first look at the evidence from empirical farm-level studies. Then we go for adoption studies beyond farm level. Later, we will present you a conceptual framework integrating farm-level evidence and system-level interaction. At the end, we will conclude the paper. So far, digital farming technologies are rarely covered in either conceptual or empirical studies, but evidence in precision farming technologies can be helpful to understand the adoption of digital farming technologies because of the similarity between the two. We did a systematic literature search and found more than 1,000 papers about adoption of precision and digital farming tools. After filtering, we reviewed 32 papers in detail. These include 54 cases. They include precision farming technologies, robotics, drones, smart farming technologies, and so on, coming from different study regions. In terms of methods, most of them use regression type analysis and a few use qualitative descriptive approaches. Then we classified determinants of adoption into 6 categories. The first one is farm characteristics, which are widely tested. For example, you can see that 43 out of 54 cases have studied the relationship between farm size and adoption, and 33 of them found a positive influence. That means larger farms are more likely to adopt new farming technologies than smaller farms. This is not hard to understand because larger farms have bigger need of efficiency and they are more likely to be able to afford expensive technology. Operator characteristics are also often studied, especially education and age, but we cannot say that they always play a role. In comparison, farmers' innovativeness, knowledge, and capacity are less studied, but showing a consistent positive impact on adoption. The role of interaction is also highlighted. For example, getting information from crop consultants seemed influential on farmers' adoption decision. Institutions like laws and environmental regulations might make farmers care more about the environment and decide for digital farming technologies. Some studies move the focus from farm and farmer to the technology itself. Here you can see that a relative consistent pattern, although the number of studies is small. Relative advantage of technology is clearly crucial for adoption decision. Complexity of managing and analyzing data that is generated from the technology, compatibility to the existing technologies on the farm, and also data safety issue are huge barriers of adoption. The last category is psychological factors. Although not many studies have considered them, they seem to be very important in terms of their contribution to farmers' adoption decision. These 3 elements, farmers' attitude, subjective norm, and perceived behavior control, are from the theory of planned behavior developed by Eisen in 1991. The theory says a person's intention to do something is a function of attitude, subjective norm, and perceived behavior control. In our case, attitude towards adoption means if the farmer thinks adopting, for example, a weeding robot is beneficial for the farm. Subjective norm means if the farmer believes other people expect him to adopt. Other people might include the family members, crop consultants, and so on. Perceived behavior control means a farmer's ability to adopt and implement the technology. Older farmers might have less perceived behavior control because the machine is too complicated to use. We know that significance does not imply the importance of a factor, which means to what extent a factor influences the adoption decision. Thus, we calculated partially standardized coefficients, beta. In this way, betas of different independent variables can be compared together, regardless the type and the range of data. Some factors have large number of observations, here marked by blue numbers, but most of factors do not. This makes it hard to interpret the results, but it is still interesting to see that education and age, although very widely studied, do not have a very large impact on adoption, especially when you compare them with farm size. Farmers' innovativeness, although with only 3 observations, shows a larger impact than other factors on this graph. Factors in other categories have very limited number of observations. We can see that subsidy and attitude have considerable impacts, but they are less studied. But farm-level studies really account for feedbacks between system elements because of methodological constraint. We see already relevance of interactions and institutions point at importance of system level. Technology attributes and uncertainty about them matter, and these are determined at system level. This requires us to look at the problem beyond a farm, but towards the system. Thus, we searched for adoption studies at system level, agent-based models, for short ABM. They are good at considering feedbacks between individual decision-making units and macro-level phenomena. In ABM, each farm can be modeled with its location, size, and so on. Each farmer behaves according to its behavior model. We did a systematic literature search and found 265 ABM papers about adoption of agricultural innovations. After filtering, we reviewed 27 ABM papers, including various agricultural innovations. We found that ABMs of precision or digital farming technologies do not exist yet. That's why we need to look at the current ABMs to know if they can provide useful modeling basis for adoption and diffusion of digital farming technologies. Adoption behavior models used in the current ABMs include economic models, cognitive models, social networks, and so on. We marked all factors considered in the model according to the 6 categories we used before. Dark color marks factors that directly trigger adoption. Light colors mark factors that are considered somewhere else in the model. Let's first read it horizontally. These 3 studies mainly consider features of farms, and the only trigger of the adoption is relative advantage, which in their case is profit of adoption. These are declassified as pure economic model. Those 3 studies are classified as cognitive model because they do not really model farms' attributes, but focus on farmers' psychological factors. There are also other type of behavior models, but the point here is that different models have different focus and limitations. If you read the chart vertically, you can see that operator characteristics are not as often modeled as in farm-level studies. And all models consider other farmers, but a few consider other type of agents, like farm consultants. Institutional factors are also seldom modeled. The same happens to attributes of technology because profit or utility is the only attributes they consider. These are limitations of ABM that we have just mentioned. All in all, current ABMs of agricultural innovations are not well connected with farm-level studies of adoption of precision and digital farming technologies. Now we need a framework that can integrate these 2 together. Adoption decision is not a one-stage thing, but a multi-stage process. Thus, we apply the model of 5 stages in the innovation decision process. The stage of knowledge is where a farmer gets aware of the existence of the technology. Persuasion stage is where he starts to evaluate if adoption is reasonable considering social, economic, and environmental impacts. Decision stage is where he decides to adopt or not. Implementation stage is where he conducts production activities with or without the new technology. Confirmation stage is where he confirms to continue adopting or rejecting. Now we'll look at the determinants of adoption at each stage. A farmer's knowledge of the existence of a new technology is influenced by the interactions with other agents like other farmers and consultants in the system, which can also influence the observability of the technology. At persuasion stage, the intention to adopt is a function of attitude, perceived behavior control, and subjective norm. Attitude is mainly influenced by the relative advantage and compatibility of the technology, which are determined by the farm characteristics. Perceived behavior control is determined by farmers' financial ability, the complexity of the technology, triability, and data safety of the technology. Those factors are mainly influenced by operator characteristics and institutions. Subjective norm is influenced by social norms and policies, which are determined by institutions and interactions. After the intention is determined, the farmer decides to adopt or not adopt the new technology. At implementation stage, production activities of the farm are conducted with or without this technology. They are connected with input and output markets as well as the environment. You can see that there are other connections on the figure, but we will not cover all of them today. Note that the red rectangles highlight the strong evidence from farm-level studies. The point of the framework is that it integrates farm-level evidence and system-level interaction and provide a modeling reference for ABM of adoption and diffusion of digital farming technologies. A good modeling framework can help us to understand the adoption of digital farming technologies and its economic and environmental impacts. Finally, some takeaways for you. First, farm-level studies identify relevance of farm and operator features, interactions, institutions, attributes of technology, and psychological factors. Second, current ABMs of diffusion of agricultural innovations are not well connected with empirical farm-level findings, and our framework integrates farm-level evidence and system-level interaction, which help us to identify gaps and conceptualize adoption and diffusion of digital farming technologies at system level. Thanks for watching.